Hey guys, I posted a video on Moodle that covers resting membrane potential. So it's in like the lab 2 folder under other resources. And if this whole equilibrium potential, membrane potential stuff is not making sense, I feel like that has a really nice visualization of how each of these things is going to change when you're manipulating ion concentration inside and outside of the cell. If for some reason this is not making sense though, which is totally fine, I wanted to do kind of an overview of how you can make sense of all of this, because I feel like it can be confusing at times. So I'm no artist, so don't judge, but let's say that this is our cell. It's beautiful, square. And usually in this cellular, between intra and extracellular content, right? We're usually going to see that potassium has a higher concentration on the inside of the cell than it does on the outside. Okay, so in that respect, red is representing my potassium, and we expect it to be high on the inside and low on the outside. Okay, I'll use blue as my sodium. Okay, in which case sodium is also a positively charged ion, but usually its concentration is just the opposite of potassium, where it is high on the outside and low on the inside. Okay, so when we are considering membrane potential, we usually notice that the inside of the cell is negatively charged. So on the outside of the cell is positively charged. So I'll use that. Oh, just kidding. I'll use green to kind of indicate the charge on the inside of the cell and the charge on the outside of the cell. Okay. And the way that we get this negative on the inside of the cell is through other negatively charged ions and other proteins that we don't really mention, because the big thing that's going to be altering membrane potential within the cell is fluctuations between these positively charged ions. Okay, so that's why we kind of concentrate on those. With that being said, if I draw another beautiful cell, okay, two things kind of constitute equilibrium potential. Okay, so I'm going to just write it like this. Okay, and let's say that we are looking at potassium. Okay, so there's two forces that are going to kind of determine the movement of potassium in and out of the cell. Okay, so again, I'm going to use my red for my potassium. Okay, we know that it exists at concentrations of high to low, right? Or we know that it exists at high concentrations on the inside of the cell, low concentrations on the outside of the cell. This is going to create a concentration gradient, right? If you guys are familiar with movement across a membrane, typically there is a pull, a natural pull, that will try to create a balance or an equilibrium, right, of content on each side of the membrane. So we have this concentration gradient that wants to pull potassium outside of the cell. Okay, so I'm just going to put K plus out, and that is dictated by this concentration gradient. Okay, now there's another force that works on potassium as well, okay, and that's its electrical gradient. Okay, so not only are we trying to balance the concentration of potassium in and outside of the cell, but we also naturally try to reach equilibrium by adjusting the charge. Okay, so if you can imagine, when potassium leaves the cell, right, or leaves the inside, that's going to make the inside more negative. Okay, and it's this negative charge that's going to passively pull potassium back into the cell. Okay, and we call that the electrical gradient. Okay, so this electrical gradient is going to pull potassium into the cell, right? Our equilibrium potential is the balance between these two things, right? So we've got the concentration gradient that's pushing potassium outside of the cell, and we have the electrical gradient that's pulling potassium back into the cell. So finding the balance between concentration gradient and electrical gradient is what creates this equilibrium potential, or defines potassium's resting state, which is a high concentration on the inside of the cell. Okay. We can also do the same thing when we look at sodium. Okay, so now we're switching ions, right? And we know from this drawing above that sodium exists at higher concentrations on the outside of the cell compared to inside of the cell. So similarly, when we're talking about this concentration gradient, right, instead of being pulled out of the cell like potassium is, sodium is actually going to be drawn into the cell due to its constant. So I'll keep that we don't get confused. Okay, and I'm going to abbreviate just so I don't run out of room. Okay, but concentration gradient is going to pull sodium into the cell. So we can associate that with sodium in, right? And then as we are drawing sodium in, okay, the cell is like, oh my, we're getting way too positive in here. I need to be like negative, okay? Or there's too much positivity and we need to push out the sodium that's inside, right? So this positive charge that accumulates as sodium is pulled in is actually going to push it out of the cell, and that's the electrical gradient, okay? Because if you think about it, like charges are going to repel each other, opposite charges attract each other, okay? So when we're creating our equilibrium potential, right, again, it's the balance between the concentration gradient pulling sodium into the cell and the electrical gradient pushing it out of the cell, okay? I feel like the concentration gradient is pretty well accepted by students most of the time, but it's the electrical gradient that is like, what? Okay, so I'll just explain it again, right? And then we'll do it again just to cover our bases, okay? So when potassium leaves the cell, that means that there's going to be a higher negative charge on the inside of the cell. Opposite charges attract each other. Therefore, the electrical gradient is going to pull a positively charged potassium ion back into the negative intracellular matrix, right? So in this case, opposite charges are attracting, so the negative inside is pulling in positive potassium. Okay. The opposite is true for sodium, who gets naturally pulled into the inside of the cell that is usually positive, right? Usually negative, but as we draw more and more sodium into the cell, we're increasing the positivity on the inside of the cell. Therefore, in this case, positive charges are going to repel each other, and the inside of the cell is going to kick sodium out to kind of reach its equilibrium point again. Okay, so again, both of these, the movements of these ions are going to be contributing to each ion's respective equilibrium potential. Okay, so now let's look at some situations where we might be adjusting each of these ions. Okay, so situation number one, we're going to say that we're going to add intracellular potassium without changing our extracellular potassium. Okay, what might happen as a result of that? So again, we're going to start with our cell, okay? And we know that usually, usually potassium has a higher concentration on the inside, okay? So let's say that we add more potassium to the inside of the cell, okay? Add more potassium. What's going to happen as a result of that? Okay. Basically, we're increasing our concentration gradient, right? Or increasing the power of the concentration gradient by adding more potassium inside of the cell. So what happens is kind of twofold, right? We're going to end up pushing more potassium out, right? That concentration gradient is going to be stronger, right? But that also means if we're not, if we kind of think about it, we're not adjusting extracellular content, we're also going to have the need of a greater negative charge to pull potassium outside of the cell to kind of counteract that flux outside of the cell. Okay, so remember this. Oh no. Ah! Okay. Remember that potassium out is due to the concentration gradient, right? So the stronger the pull is going out, that means the stronger the pull we need from the electrical gradient going in, okay? So what this is telling us here is that we need a stronger negative charge, okay, inside of the cell to pull our potassium back in. Okay, so in this case, our K out is happening at a faster rate than we can pull our potassium in. Therefore, in order to get to our equilibrium, we need the electrical gradient pulling potassium in to be more negative. Okay, so this is what happens when we increase the concentration of potassium inside the cell. Okay, now what happens if we are fluctuating sodium? Okay, so now let's say situation number two is that we are adding extracellular sodium without changing intracellular sodium. Okay, what do we do? Right, so we've got our cell again, and we are saying let's add more sodium on the outside, which is where it naturally thrives, right? That's where we have the highest concentrations. So if we are adding sodium to the outside, right, it has a natural concentration gradient to pull inside the cell, right? So this driving force is going to be increased, right? because sodium's is like, I need to balance myself out, right? And there's too much on the outside. So if we put more sodium on the inside, then I can reach an equilibrium. Okay. But then if we think this is happening as a result of our concentration gradient, what's going to happen to the electrical gradient, right? If we are increasing positivity by drawing sodium in, that means that we need to create a greater positive charge on the outside of the cell to push sodium out, right? But also, this increased positive charge is naturally going to say, no, right? And our electrical gradient is affected in that way, right? So by having greater positivity on the outside, we increase the concentration gradient, pulling sodium into the cell. That's therefore going to affect the electrical gradient by increasing the repellence. I don't know if that's a word, but we're going to have increased repelling, right, of like charges. So that increased positivity is then going to say, nope, I'm going to strengthen the electrical gradient and push sodium out of the cell. Okay. So what technically happens to our equilibrium potential is that in order to maintain equilibrium, right, we have to balance our in versus out. So the electrical gradient, therefore, right, because what we have when we start is that Na in is greater than Na out, right? That's what happens when we fluctuate extracellular content. So what we need to happen is our electrical gradient needs to be stronger. Oh my God, what is happening? Our electrical gradient pushing sodium out needs to increase, right? To be more positive so that we are pushing sodium out of the cell at the same rate we're drawing it in to maintain that equilibrium potential. Okay. So that's kind of a snapshot of how all of this makes sense. Okay. Additionally, I did want to go over permeability because I feel like that's another thing that gets a little confused sometimes or confusing. So when we think about permeability, always notice like it's harder to write or spell when you're being recorded. But permeability, right, in terminology wise, right, it's the ability of an ion to passively, and this is the key word here, passive, not active, right, passively move in and out of a cell. Okay, I'm just gonna abbreviate here. English is overrated. All right, so typically, right, we would have more or greater permeability of potassium than sodium. And the reason this is because there are more potassium channels. Okay, so we're gonna give two different scenarios here. Got my cell, right? And then scenario one, we're going to talk about on the right side of the cell. Scenario two, we'll talk about on the left side. So first, let's consider what normally happens, right? So we already covered that for the most part, charge on the inside of the cell is negative and charge on the outside of the cell is positive, okay? And we have natural movements of potassium, right, due to its concentration gradient, pulling it out of the cell, right? So that's natural movement out, right? And sodium has the opposite, where it naturally rests outside of the cell and will have natural movement into the cell. Okay. So part of the lab is to say, like, okay, what if we change the permeability? Right? So this is the passive movement. That's just what naturally happens due to the concentration gradient. Okay. But what if we change permeability? So that's our second scenario over here. Okay. Let's look at sodium first. Okay. If we change the permeability, let's say we are increasing permeability of sodium. Okay. If you hear jingle bells, that's my cat. Sorry. Okay. If we increase permeability of sodium, that means we are going to increase sodium's movement into the cell. Okay. What happens when we move more sodium into the cell? It becomes positive. Okay. Now, what if we did the opposite with potassium, which usually lives inside the cell, right? And let's say that we decrease the permeability of potassium. Okay. That's going to decrease its movement out of the cell, right? Because potassium generally likes to move out, right? But if we decrease the permeability, we decrease that ion's ability of passively exiting the cell due to its concentration gradient, we're limiting how much can actually move. Therefore, we are also going to end up with a positive charge building up, right? Because if we're not letting potassium move out, we're increasing positivity. Okay. Similarly, if we allow too much sodium in, we're increasing positivity. So changing the permeability is going to change the membrane potential. Okay. And then the last thing I wanted to note with this stuff is that it all goes together, right? Or the way that we kind of modify our membrane potential is one, through the permeability, right? So how much we allow passive movement. And passive movement, right, is going, that's like, think our concentration gradients, is going to affect our electrical gradients, right? Which we talked about in these two things here, right? So the more we change our concentration gradients, the more effective our electrical gradients are to try to balance out that equilibrium potential. Okay. And if we're balancing equilibrium potential, that means we're going to have some changes in charge on the inside of the cell, which should be natural, right? So when we have an action potential, usually that means there's a flux of sodium into the cell, which causes the increase in positivity. Okay, and then there's a whole slew of things that happen after that that will pull potassium back in. Okay, so changing the charge on the inside by certain processes, like when we get a signal from another neuron, are going to change the charge. That's going to affect how ions are pulled in and out of the cell, right? And then that effectively changes the charge on the inside of the cell, as well as the outside. But inside is usually what we are measuring when we're looking at membrane potential. Okay. But with this being said, we can't rely on passive movement. Okay. So there is another mechanism that will help us keep this membrane potential, where we have this negative charge on the inside of the cell and the positive charge on the outside of the cell. Okay, and that's our sodium potassium pump, right, which is an active transport protein, right, or a protein that encourages active transport, you can say that way, right? And a certain number of potassium ions are passed into the cell from the outside, a certain number of sodium ions are passed to the outside of the cell, right? Because through these equilibrium potential mechanisms up here, right? I meant to make a star, but it didn't happen. Okay. through these equilibrium potentials up here, if we just let passive stuff work itself out, eventually we would have equal charges on the inside and outside of the cell. But we know in order to make sure that we can detect certain neural changes or neuronal activity, we need to maintain this imbalance in charge where we have negative outside and positive inside. That's what allows us to be able to have changes like in muscle activity or other organ function. Okay, so hopefully I can zoom out on all of this, right? Hopefully that all makes sense. And if not, I'm always happy to answer questions in office hours.